Hello and welcome to another session in physics. In this session we'll be looking at the topic vector and scalar quantities, distance, displacement, speed and velocity. But before that, let's review the previous lesson. At this point, I'd like us to talk about the definitions of scalars and vector quantities. When we talk about a scalar quantity, we're simply referring to a quantity that has just magnitude but no direction of any kind. Typical examples of scalar quantities are things such as time, distance, speed, temperature, volume, work, power, electric potential. And I'll tell you why they're classified as scalar quantities. When someone asks you what time it is, the person is just asking you to tell the time is on your watch, where you have your clock looking like this, but you don't have to tell the person the direction of the clock hand. You just tell the person, for instance, the time is 3 o'clock. But you don't have to tell the person the long hand is pointing towards north, the short hand is pointing towards east or west. You just tell the person what time it is. And if someone asks you what is the distance between A to B, let's say the distance is 3 meters, for example, you don't tell the person 3 meters in the northwest direction or 3 meters in the south direction. There is no direction. Or if someone asks you what speed are you traveling at, you could tell the person I'm traveling at the speed of 5 meters per second. You don't have to tell the person the speed of 5 meters per second in a southwest direction. No, that is what scalar is about. Scalar is only concerned about the magnitude, the value of the quantity, and no direction is required. So we say that scalar quantities have no directional components. They only have magnitude. Additional examples of scalars are things like density, mass, and energy. On the other hand, vector quantities are the exact opposite of scalar quantities. Remember that we said scalars have no direction, but they have only magnitude. But in this instance, vector quantities have both magnitude and direction as well. Examples of vector quantities are velocity, displacement, acceleration, force, momentum, moment, and electric field intensity. So when we talk about those, we are looking at not just their magnitude, but we're also looking at their direction as well. So we use arrows to represent vector quantities. Now let's talk about the position of an object. The position of an object simply refers to that point in space which that object can be located, or a particular place where objects can be found. I'm sure you must have heard about GPS systems. GPS systems use what we call coordinates to tell us the exact position of objects in space. It might interest you to know that anybody, any object, any material, any quantity in space has its exact position, and that position is given by means of coordinates, which is made up of numbers and using the north, south, east, and west systems of positioning, our cardinal points. As you can see from the graph here, you'll see that we have two coordinates. We have the x coordinates and we have the y coordinates. The x coordinates on the x-axis, the horizontal coordinates, they are called the abscissa, while the y coordinates are called the ordinates. The y coordinates are the vertical coordinates. They are called the ordinates, while the x is called the abscissa. At this point, let's look at distance and displacement. When we talk about distance, we're simply referring to the gap between any two positions in space. For example, point A and this is point B, there is a gap, there is a space left in between here that separates A from B. That is what we call distance, noted by S in physics, and its SI unit of measurement is meter. Like we mentioned earlier, distance or length is a scalar quantity because it has nothing to do with direction, and it is calculated when we multiply average speed and time. That gives us distance. On the other hand, displacement, distance sort of, but it is distance covered in a specific direction. Okay, And because of this direction, we say that displacement is a vector quantity, while distance is a scalar quantity. So the basic difference between distance and displacement is that distance is a scalar quantity and displacement is a vector quantity as well. And that's why when we come to things like velocity, velocity is given by displacement time. On the other hand, speed is given by distance over time. Both of them are measured in meters per second. So if someone asks you, what is the basic difference between velocity and speed? The basic difference between velocity and speed is that velocity is the ratio of displacement to time. Therefore, that makes velocity a vector. On the other hand, speed is a ratio of distance to time. Because of this distance, it makes speed a scalar quantity. So displacement, like we said, is average velocity by time. At this point, let's see how we can use bearing to indicate direction and displacement as well. We say that the bearing of an object from the origin is the angle that it makes with the North Pole in the clockwise sense. In a mathematics class, you also talk about extensively. But I need you to know that we have 4 main cardinal points. The one pointing in this direction is called the north. This is the east, this is the west, and this is the south. In between, we have the northwest direction, northeast, southwest, and southeast. So we use all these cardinal points to show direction and displacement in space. How about speed and velocity? Speed is defined as the rate of change of distance that has been moved in an unspecified direction, or the rate of change of distance per unit time in an unspecified direction. And like we said, it is measured in meters per second. So distance moved is measured in meters, time is measured in seconds. That is what gives the mathematical expression of speed as meter per second. How about average speed? Average speed is given when we have the ratio of total distance traveled to total time taken. So all we just have to do is we look at final distance minus initial distance, like S2 minus S1 over final time T2 minus T1 initial time, and that gives us our average speed. It's important for you to note that when we talk about uniform constant speed, it simply refers to when a body covers equal distance of time in equal time intervals, however infinitesimally small that. On the other hand, velocity is defined as the rate of change of displacement or distance moved in a specific direction. Okay, understand, speed has nothing to do with direction because it is a scalar quantity, but velocity has everything to do with direction because it is a vector quantity. This is an example of sample velocity time graphs. When for this first one, for example, this is showing a velocity time graph of a body moving with constant speed. You can see it here, moving with constant speed. Already the body is in motion, but it is moving with constant speed. For the second one here, you would see that this is a body that is accelerating from rest. The point 0 is, but the body has started moving, and this motion means acceleration from rest. The third velocity time graph shows a body decelerating to rest. Decelerating means that brakes are being applied, so it is trying to come down from a very high velocity to rest. In other words, possibly the car saw a policeman at the checkpoint and it started applying brakes until it had to come to a halt. And the same principle also applies to the last time graph as well. Alright, so let's talk about uniform constant velocity. We say that an object is undergoing constant velocity if the rate of change of displacement is constant, no matter how small the time interval may be. So we have an example here on the slide about a train moving with a speed of 54 kilometers per hour for 1/4 of a minute, and we're asked to stand that has been traveled by the train. You will agree that the speed here is 54 kilometers per hour, which when we convert it to seconds, we're going to have our speed as 15 meters per second, And our time, they said our time is 1/4. 1/4 means 1/4 of 1 minute, which is 60 seconds. So when you multiply 1/4 by 60, we're going to have 15. And then the distance s is going to be given by speed times time. So our distance traveled by the train is going to become 15 meters per second, which is the speed, times 15 seconds, which is the time. We're going to have 225 meters, and that is the total distance that was covered by this train. And now let's talk about acceleration and retardation. What do we mean by acceleration? Acceleration is defined as the increasing rate of change of velocity with time. Increasing rate of change of velocity with the time taken. So when the velocity of a body increases in equal time intervals, no matter how small the time interval may be, we say that the body is accelerating uniformly. The opposite of acceleration is what you see here, retardation. Another name for retardation is negative acceleration. Another name for negative acceleration is deceleration. It simply means accelerating to rest. This time around, the speed is not increasing, the velocity is not increasing, but it is reducing. And retardation is given by decreasing velocity change over time taken. So more like v2 minus v1 over t2 minus t1. Now these are some equations of uniformly accelerated motion. We have v equal to u plus at, s equal to ut plus half at squared, v squared equal to u squared plus 2. We can also use these three equations of motion to solve questions on accelerated motion. We can use them to solve questions on accelerated motion. Let's take one example here. It talks about a car that moves from rest with an acceleration of 0.2 meters per second squared. And we're asked to find its velocity when this car has moved the distance of 50 meters here. So the most appropriate equation to use is the last equation of motion, which is v squared equal to u squared plus 2as. Now remember from the question that find the velocity, the final velocity, and the equation says u squared. U squared is initial velocity, but the question says the car moved from rest. So the initial velocity of the car was 0 since the car was starting from rest. So 0 squared plus 2 times a, the acceleration, which is 0.2 meters per second, times our distance, which is everything here is going to give us 20, because 0 squared is equal to 0 and v squared is equal to 20. But we're not looking for v squared, we're looking for v. Be the subject, all we just have to do is find the square root of 20, and the square root of 20 gives us 4.47 meters per second. That is the velocity. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.